Fly at
It's
race.
terrible.
I've never seen that.
I don't understand it.
I'm sure she doesn't.
She
But
doesn't take it, but I'm just going to listen to
did she take
I
it?
left you with some homework.
Yes, I am so prepared. Shane, I'm so happy you're sitting next to me.
I know, man.
Man,
Did you
this is
figure
what needs to happen.
Did you figure those out?
Yeah.
100%.
I definitely looked at it at home.
Did you, Dan?
We only got
One.
2 of them.
And CH3 is a 3.
Yeah, we only had 2.
No.
No, one more.
And then the other one was.
Careful what you say, because this whole being recorded. I didn't hear what you said.
Oh
And then the other one
I just heard the blah, 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 crazy, so.
2 methyls. They were on the bottom double bond. I don't know if it matters.
One was here. One was that.
No, they were. They
We're
were.
right next to each other.
This is
That's
to
the
each
one.
other.
Going to the left.
This is for.
Is that it?
On the left is the 6 o'clock.
Well, it doesn't matter.
On both the double
It
bonds.
doesn't matter. It doesn't matter. Wait.
That's
Oh, it
there.
doesn't matter.
Yeah.
They were
Oh,
both.
it does matter.
Yeah.
Oh,
Double bond,
shoot.
yes.
Right there.
That was it.
There we go.
You erased the third one.
So they were, okay.
Yeah,
All right.
it's too hard and you were
Yeah.
You said you don't want to mess with that.
Oh, okay. Well, I did, but not, I don't want, I wanted some of you to come back. So what's the name of the first one?
3-chlorotoluene?
Would be an adequate name. It's actually the well, it's not the system. The systematic name would be 3-chloro-1-methyl-toluene. But we've decided, methylbenzene. We've decided that methyl changes the name of the ring. Because toluene is a widely available molecule in its own right. It's a solvent. It's that smell of paint, oil-based paint and oil-based adhesive. It's the one that people sniff on purpose to get a high. Don't. Just don't. Because it's really, really, really bad for your brain. So that would be, what's this relationship? So instead of using the number, we're going to use the relationship. Okay. Next. The methyl is now part of the new name. That's it, we have 2 types of substituents. Substituents that don't change the name of the benzene ring, and then substituents that do change the name of the benzene ring. And the methyl was in the camp of substituents that do change the name of the ring. So a methylbenzene is now a toluene. You count that methylbenzene now as a toluene unit and only tell me what the chloro is. What about this? That relationship is ortho. How can it be methyl toluene? Because putting a methyl onto the ring changes the name from benzene to toluene. So which one of these methyls is the toluene and which one would be the methyl? So calling it methyl toluene, well, now I'm in a quandary. Which one of them is toluene and which one of them is a methyl? This is where it all goes horribly wrong. This is the ortho. So nobody bothered to look this up? Not a single one of you. Should never have changed the name of methylbenzene to toluene. If you'd have just let toluene be methylbenzene, then we could have 1,2-dimethylbenzene. Systematic name, everybody's happy. But no, you had to call methylbenzene toluene. So now, dimethylbenzene gets to be xylene. Oops. I will not expect you to know the names of absolutely all of these because it starts to get silly. What's the name of this?
Paranitrotoluene.
It's not a nitro.
Oh, gosh.
That's an amino group. So this is 1-amino 3-methylbenzene. Or if you're in that camp that says put the branching ahead of the functional group, 3-amino 1-methylbenzene. Either way, I hear that name, I can write that structure down. Because I've been schooled in the systematic naming of molecules. But changing the substituent from a methyl changes the name of the ring to a toluene. So surely this is 3-amino toluene. But changing the substituent on the benzene ring to an amine makes the ring an aniline. So which one is it? Is this a methyl aniline or is it an amino toluene? Because you went with the trivial name, you now cannot use the systematic name.
Is it parent?
That's now a toluidine.
Stuff up.
I know.
Harry Potter spell.
Yeah. What about this one? I'm going to put this under just a general heading, some non-systematic naming systems are stupid.
It's like a para-toluene.
There's a benzene, you put a methyl on it, that benzene becomes a toluene. So this should be hydroxytoluene. Oh, but putting a hydroxy on the ring makes the ring a phenol. So is this methylphenol or hydroxytoluene? No. No. That's a cresol. Kind of stupid. Okay, and here's where the stupidity kind of climaxes because the ortho-meta-para stuff, fabulous for telling us the relationships. And honestly, there is a point where ortho-meta-paras are a little bit like cis-trans. It gives you a quick view of, you realize ortho-meta-para. You kind of get a quick understanding of what the relationships are. And numbers are difficult to comprehend sometimes. But you need the numbers in order to have a full understanding, and a systematic name is always going to be better than a trivial name. Okay, what's that? ortho nitrotoluene. All right. What about that one? Name?
It would be orthodinitrotoluene.
Nope.
Two, five, nitro.
Yeah, sound good. Ortho.
The methyl changes the name of the ring. Where's carbon number 1?
On the metal.
Not on the methyl.
Not on the carbon attached to it.
Mm. The ortho and the meta and the para have outserved their usefulness because they can only describe the relationship of two objects. Ortho, meta, para can only describe two positions. So that ortho, meta, para notation is only two substituents. Okay. This has 3. Yeah. This has 3, therefore it can't use the other notation. So ortho, meta, para, nice, cheap, cheerful way of describing molecules, but has a real limitation. This molecule would be
2, 4, 6.
2, 4, 6. And when I was being taught organic chemistry, we really didn't do the ortho, the meta, and the para. We just didn't. We called things 1, 2, 1, 3, 1, 4, and 2, 4, 6 is a pattern that you get to recognize. This is 2, 4, 6. Try. Nitro.
2,
What's
4,
that?
2, 4, 6 trichlorophenol.
It's 2,4,6 trichlorophenol. Trichlorophenol, not really sold in this country, but is widely available in Europe as a little brown bottle that if you had a sore throat, you'd go to the pharmacist and you would get a bottle and it says TCP on it. And TCP could be used as mouthwash to kill the unsavory bacteria in your mouth. Or you could put it on the floor and with a mop and bucket and mop your floors with it. Which is coincidentally where Listerine started. Listerine used to be floor wash. And then they realized they could make more money if people gargled with it than they were ever making getting floors clean. So they rebranded Listerine as a mouthwash, but it started life as a floor cleaning product. If the person next to you in lab is making TCP, maybe they have a sore throat. Maybe they're concerned about the state of the floor. What should you do if the person next to you in lab is making 2,4,6-trinitrotoluene?
Run away.
Run away!
There's TNT.
Because just as that's TCP, this is TNT. Run. Tell others on your way if you like. Call the police from a safe distance. Okay. So the naming of these molecules is kind of ad hoc, made up. There is a systematic name that underlies all of these, but not everybody uses it all of the time. Okay, let's go make some. And we know most of the reactions needed to make most of the materials that are just made. All right, let's think. You can write all the mechanism out if you want to, or you can just write the arrow with the reagents and conditions. I want you to take benzene, and I want you to convert it into this. Off you go. You may confer amongst yourselves. Don't be an island. Don't think that you have to do this on your own.
That's cheap.
All right. So while you're thinking, I will murmur. Look at the reactant. Look at the product. How many group things are in the product? There's 3 things to my product. There's a benzene ring, and then there's a chlorine, and then there's a nitro. So I need 3 things to do my reaction. One of them is given in the question. So this disconnection approach that Elias Corey made popular with retrosynthesis means to make this molecule, as yet unnamed, to make this molecule, I need a benzene ring, and I need a source of chlorine, and I need a source of NO2. Now, knowing a little bit about these reactions, I know that each of the things that react with the ring are going to be electrophiles. So I need a source of Cl+, not a source of Cl-. And I need a source of NO2+, not NO2-. So not the nitrite ion, that you learned about in general chemistry. Ite meaning negatively charged, but with one less oxygen than nitrate. So nitrate would be NO3 minus, nitrite would be NO2 minus. And that would be a plausible thing to stick onto this ring, this connection approach. Hey, how am I going to find an NO2? But no, we already know that that reaction needs an electrophile, so I need NO2 plus. So I need two reactions. And they're in your notes.
How do you target a specific carbon
That's what we're
chain?
going to do next.
Oh, 'cause the
We're going to
H2SO4 is strong,
discover.
so yeah.
Rather than me just tell you, we're going to discover it, and it's going to be
Man,
a
Jake, you are
surprise.
ridiculously
CO2
smart.
and CO2.
Okay?
What is wrong?
Right,
Yeah, so
HN3.
it is
How
weird.
come?
Hmm.
H2S with the CO.
H2SO4.
So
Okay.
the-
Which on the night?
you
And
use
of course,
You use H2SO for channel.
of course, here's the trick.
Which one comes first?
Which substituent went on first? I've got two substituents. I'm going to do the reactions back to back. And here's where, I never took a psychology class, but if I did, I would be slightly more evil than I already am. A small amount of psychology that I already know tells me, when you look at this in your brain, that's more important than this, because that's at 12 o'clock, and the thing at 12 o'clock must be the most important thing. No. No one said that. Okay, how are we going to do this?
HN3.
So which one are you going to do first? Okay, let's do the nitro first. On my condition.
HNO3 and H2SO4.
HNO3 concentrated at H2SO4. That does in fact generate this little nitrosonium ion right here. And so my first reaction gives me this.
We don't have to draw like the hydrogen dropping that way.
Now, if you want to write the mechanism in, yeah. I said, we've got all this real estate. If you wanted to write the mechanism in, go ahead. But this is just asking, how do I get from here to here?
Okay, cool.
So that's two consecutive reactions. And then my second one
CO2.
was Cl2.
ALCO.
Now, AlCl3, we said a couple of times, is the real hard-hitting Lewis acid catalyst. I'm going to introduce you to a newer one, FeCl3.
Did you know that? Or did you read that?
Not as strong as AlCl3. If you want to keep the AlCl3, keep the AlCl3. Don't particularly care. It still gets the job done. But it might interfere with other things. One of the things that we're going to learn as we go is that if there's only one thing reacting in your molecule, then it doesn't particularly matter what you use. But if your molecule has multiple sites for reactions, at some point you want only the site that you are currently thinking about reacting. So if you're using something very powerful, that might interfere and do some side reactions that you didn't use. So telling you that now is an option. That's probably going to be the Lewis acid catalyst I personally use on the exams. Interchangeable with these, but that one's more powerful. Okay, and then that puts, there's my nitro. That puts the chlorine here. Oops, wrong.
Can we go over why it goes there?
No. Let's get to what first.
Yes, I was ready to say something. That's why I look at you for so long, to make sure that it's gonna stay there.
What you guys can't see is occasionally I will look into the audience.
I'm
Go!
I don't know if you're gonna keep it there.
This. What?
I'm lost.
Yeah. Okay. There are two types of substituents. Those that make the ring want to react, and those that tell the ring that it already does not want to react, don't react anymore. Just stop it. The difference is the substituent either pushes electrons into the ring or it pulls them away from the ring. There are two types of substituents. And only when the substituent is on the ring can it have this influence. So don't think, well, I'm doing a chlorinations. Chlorinations are activators. They push to the ortho para, so I'm going to put this to the ortho. What's already on the ring determines where the next electrophilic aromatic substitution occurs. This is a huge deal, but it's easy to solve. So the substituent already on the ring. Directs the location of the next electrophilic aromatic substitution. Okay? This has become known as a directing effect. And directing effects have a big, big consequence on what it is that you make, and they must be taken into account before you start spending money. I needed to make chloronitrobenzene. I bought all the equipment and all the chemicals, and I just went ahead with 2 reactions that I figured out, but I did them in the wrong order. And instead of making the ortho-chloronitrobenzene, I ended up making the meta-chloronitrobenzene, and now I'm gonna have to find a market for it.
Why wouldn't it be, this, where you set up what it would be?
So this one is meta, and that one is ortho, and I'm going to describe now in a little table how to predict which is which. Okay.
Quick question.
Yeah.
That probably doesn't matter, but so when you did the chlorination last time, you had I know the CL, like where the NO2 is up there, that's how you drew it the first time.
I wrote the NO2 here to fake you out thinking that you were going to get this.
But on the bottom,
Uh,
why can the CL be able to
This first substituent,
It doesn't matter where it is.
I can write it in absolutely anywhere I want to.
One.
Yeah.
Because there's only one. I can write it wherever I want to. That nitro could be here. Now, when I'm typesetting the exam, I realize that if I make my characters this tall, it requires more space. So for the mono-substituted materials on the test, they're usually there. Unless I'm being mean. If I'm being mean and I want to say, look over here, everybody look over here, while I'm taking the money out of your purse. Look at this hand. I'm going to put something at the 12 o'clock position because everyone's feeble human brain is going to say, 12 o'clock position. 12 o'clock position, people. That must be the most important one. And no, it's not. Everything is up for conversation.
So you're gonna show us what the most important ones are?
Hmm?
You're gonna show us what the most important ones are?
I'll show you how to figure it out. Directing effects fall into two categories. One, electron donating groups. Electron donating groups push electrons into the ring. Now remember, the benzene ring doesn't want to react. It's very, very stable. What do you think pushing more electrons into the ring does to the ring?
Makes it less.
Makes it more unstable. Now it has more electrons, means it wants to react a bit more. So pushing electrons into the ring activates the aromatic ring to react with electrophiles. Electrophiles are positively charged. If I push more negative into the ring, now the ring becomes more of a nucleophile. It's easier to reach out to electrophiles. I can do this one of two ways. So, part A of electron donating groups. Is called induction. What this is pushing electrons down a single bond. This is the exact opposite of electronegativity. Electronegativity is something that we have defined quite well. It is the ability of an atom to pull electrons towards itself within a covalent bond. So we think of two atoms bonded together by a single bond, and one of them is pulling electrons away from the other. That would be a minus I inductive effect. This is the exact opposite. This is the plus I inductive effect, and it is an atom attached to another atom, and this atom is gently pushing its electrons towards this first atom. look to the periodic table and find a candidate on the periodic table for an atom that I might have attached to my benzene ring that would push its electrons away. Where might I find an atom that pushes its electrons?
Boron,
Okay, boron. Why'd you pick boron?
because it's a non-metal and it pushes electrons, it's on the left side of it.
It's a non-metal, so we're looking for a covalent bond, and it's a non-metal, and it's on the left-hand side of the periodic table. Okay. We don't have that much boron chemistry. There's very little boron chemistry in the textbook. Find another one. It's near boron.
Is it silicon?
No.
Is it carbon?
Methyl groups gently push their electrons away. That's how, remember, they stabilize carbocations by pushing electrons towards them. That pushing of electrons is the plus I inductive effect. In fact, any R group. R by now means some carbon-containing group. Okay? Anything alkyl. All right. The other thing. So this is a very weak effect, and we tend not to see it have an impact over anything other than a short range. If we push electrons towards a carbocation by surrounding it with carbons, okay, but we don't feel that effect really more than one bond away. The other effect that will donate electrons into the ring is much more profound. It is called resonance. And this is now much more wide-ranging and powerful. So if I am looking for a substituent that goes onto the ring here, this candidate can always spot an electron donating group because the atom directly attached to the ring has a lone pair of electrons. Okay? So all we have to do is make a list of those atoms that we can find on the periodic table that have lone pairs of electrons, and then make rational substituents out of them based on the correct number of bonds that the Lewis structure for that atom predicts. Okay, look to the periodic table. Tell me an atom on the periodic table that has a lone pair of electrons.
Nitrogen.
Oxygen, nitrogen,
I said oxygen.
oxygen,
So,
sulfur,
Fluorine.
fluorine, chlorine,
Bromine.
bromine.
um,
They all make one bond at a time. These all have a lone pair of electrons on the atom that is directly attached to the ring. These will all activate the ring. They will activate the ring to further reaction by pushing their electrons in. Okay, that's all the things that make one bond. Let's think about the things that make two bonds. What have I got?
Oxygen. Sulfur.
If I add an OH to my ring, what am I? You're a phenol. Adding a chlorine to the benzene makes chlorobenzene. Adding a bromine to the benzene makes bromobenzene. Adding an iodine to the benzene makes iodobenzene. Adding a hydroxide to the benzene makes a phenol. Going to change the name. Instead of using the alcohol, what if we use the ether? Instead of using an oxygen, you could use the sulfur version, and alcohols now become thiols. Thiols are supremely stinky, really, really wretched, bad smells. Okay, what else? Those are the two bonded stuff. Let's look at the three bonded stuff. If you put an amino group on the ring, you're now an aniline. And it doesn't have to be hydrogens. It could be one carbon. Or it could be two carbons attached to that nitrogen. Okay. We're going to do this multiple times, and it is big and it is ugly, but you will get used to it. First of all, you're going to resist it because it looks like a lot of information. But this is everything that we need to know for activators. We're going to spread this. There's a weekend between this and the deactivators, which are going to come on Monday. It's going to have time to a little bit to sink in. Don't panic. This is going to feel like a lot of information. Pick one thing from this list.
dial.
It's the only one I'm never going to show you again. Do the phenol. Thiophenol, lovely molecule. Smells like a gas leak. Going to take this molecule, phenol, and I'm going to resonate it. What were my rules for resonance? Move a what to a what? what comes at the very top?
Negative
Move a negative
to a positive.
towards a positive. I don't have a negative and I don't have a positive. Then what came next? Move a lone pair towards a positive. I don't have a positive. Stop talking about positives. Move a pi bond towards a positive. I don't have a positive. Then
Negative to a pi.
move
Negative to a lone pair.
lone pair of electrons to a pi bond. That's what I've got in this molecule. I've got a bunch of pi bonds and some lone pairs. I don't move the pi bonds to the lone pairs. That would be silly. This is going to look like a lot of information. But every time you do this, it's the same thing. So you can look at it and recognize it and know that you're doing it right, and know that somebody else has done it wrong. Going to move electrons from the lone pair, not to the pi bond, but towards it. This carbon at the 12 o'clock position already has 4 bonds. I'm making a new bond to it. What do I have to do? To get rid of a bond, I have to break a bond. Which bond breaks? The weakest bond breaks, and the weakest bond is the pi component of that double bond. Where does it go? It ends up on that carbon. What's it going to be when it gets to be on that carbon? It's going to be a lone pair of electrons, which is going to look like an anion. So, the first, remember, resonance, none of the atoms move place. All of the atoms stay exactly where they are. This pi bond has not moved, that pi bond has not moved, but I now have a negative charge on that shouldered carbon there at 9 o'clock. The first thing that you do in any resonance structure is you establish a double bond from the substituent to the ring. Actually, if I say that, if you write it down, it's true in absolutely every case if you word it this way. Establish a double bond between the substituent and the ring. I've given this one a direction. Monday, we're going to see the arrow come the other way. Okay? Now I have a double bond here. If I didn't have a double bond here, everything is wrong, and everything else that you write after this is also going to be wrong. Fact check. Did I make a double bond between the substituent and the ring? What's missing from my sketch?
Positive on the oxygen.
That oxygen needs a positive charge. Okay, to make that positive charge go away, could I take that negative, put it back between those carbons, and push the electrons up here? Could I do that?
Yeah.
Yes, I've already described it. It's the backwards part of this arrow. I've already described it. So it's not part of my answer, because I've already said that that's possible. Whatever I'm going to do next is something else. But what I'm going to do is I'm going to make this negative meet that positive, but it's going to go all the way around the ring to make it happen. Rules for delocalization. Take a negative charge and move it towards the pi bond. That makes the pi bond move. In this sketch, all your pi bonds are symmetrical. kind of symmetry is that?
Yes.
Should be one person in the room who knows what kind of symmetry that's going to be.
It is C2.
That's C2 symmetry. You would know that? If you'd signed up for inorganic chemistry. All right. Oh. That's a negative. There's my positive. Do you remember what I said at some point about resonance always stabilizes the molecule? Yeah? If you can move the electrons around in the molecule, that is always a stabilizing effect. What goes with that is the more times you can do it, the better the stabilization gets. Last one. I end up with the phenol again. Somewhere in the middle, see where that symmetry is? Everything on this side and everything on that side is a reflection. Left hand side. LHS, left hand side. Everything on the right hand side of your sketch should mirror what went on the other side. Okay, if I add these all together, I get the net resonance hybrid. I'm going to need to go over by a minute. If I look at what effect moving all the electrons around in this molecule has had. Some of the time, the bond between the carbon and the oxygen is a single bond. It's a double bond, it's a double bond, it's a double bond, it's a single bond. Some of the times there's a positive on the oxygen. So there's a little bit of a charge on that oxygen, and some of the time that's a double bond. And some of the time this is a double bond, and some of the time this is a single bond. So each of these bonds has partial double bond character. And when I look at this carbon, the ortho carbon, sometimes it's negative, sometimes it's not. So there is a little negative charge on that carbon. Here, at the meta position, there is never a charge. Here, at the para position, sometimes there's a negative charge. Here, at this meta position, there is never a charge. But here at the other ortho position, sometimes there's a negative charge. So that ring has 3 partial negative charges in it, and we are expecting it to react with electrophiles. Guess where the electrophiles react? Electrophiles are positive. They're going to react here, here, and here. So electrophilic aromatic substitution occurs at the ortho and para positions. Activated rings do that. Deactivated rings do something completely different. We'll see it Monday. Okay.
That makes sense. I was trying to
We'll
figure
do
out-
it. We'll
I was-
do multiple examples.
I
of
don't
it.
understand how that's like the order though, like the
One's a chloro, and one's a nitro. We haven't seen what the deactivating groups look like. Deactivating groups have high bonds. And a nitro group has high bonds.
What the hell are we doing? Oh, you were throwing it, I was like, why does this matter? We went back to the beginning.
So you wanna go learn about catnip?
Go read your mom.
The cat's
Version 1. Version 2 will probably pop up.